Okay, so what we're going to be doing next is a weak acid base titration, strong base titration, and that's going to be between chlorous acid and sodium hydroxide. So these calculations are going to be a little bit more difficult, but we're going to set them up exactly the same way. We have 25 mils of 0.1 molar acid titrated with 0.2 molar sodium hydroxide. We're going to calculate the pH at all these different points, okay? So here's the first one, 0 mils, right? It's just a concentration, it's the weak acid calculation. Now, this is a relatively strong weak acid, so we are going to have to set up an ice table and solve for the concentration of hydronium. So we'll go ahead and set that up. I'm going to say HA. Again, this should be very familiar to you from the last chapter. And H2O, and then H3O plus A minus, right? And we'll go through that whole process. Now, you know, if you're really familiar with these, what you recognize, and I'm not going to actually finish this, but you'll be Ka is going to be equal to x squared over 0.10 minus x. And then we looked up the Ka value. This is the expression you should end up with, 1.1 times 10 to the minus 2, like that. So we'll go ahead and run that through a solver. And that gives me a value of hydronium, or X, right? Sorry, X, of 0.02881 molar, 2 sig figs here. So then my pH comes out to be 1.55, like that. Okay. Now, you know, if you compare that to what we got for the strong acid, which was 1, it's a little bit higher, so because it's a weak acid. Okay, so the next thing we're going to do is do the next calculation at 10 mils. And again, we're going to set this up exactly the same way, but we have a few more things to keep track of. Again, total volume, right, is going to be 35 milliliters. My moles of acid will be the 225 times 0.1, so this is 2.5, and this is millimoles, right, in this table. Well, I should put it over here, but I want to use this space. I'll just write it really small. For the sodium hydroxide, right, that's going to be 2.0 millimoles. So the exact same calculations that we did before. And then this is going to be minus 2.0 minus 2.0, and this is going to be 0.50 or 0.5, and this one's going to be 0. Now, here's the deal. This is the conjugate base of a weak acid, so it has an effect on the pH, and because it's a weak acid, we have to do an equilibrium calculation, right? So what we're going to do is say that this was 0 at the beginning, but this one's going to be plus 2.0. So now what we have is 2.0 millimoles of the conjugate base, 2.0 millimoles of the conjugate base at that point in the titration. Again, the water will ignore because it's a liquid. Well, now what we have to do is we have to do the equilibrium calculation. And to do that, what you're going to need is you're going to need the molarities of the acid and its conjugate base. So the molarity of the acid is just going to be 0.5 over 35, exactly the same that we did for the strong acid strong base titration. That'll cancel and get moles per liter. So I'm going to end up with that's 0.01429 molar. And I'll do the same thing for the A minus, and that's going to be 2.0 millimoles divided by 35. And then that leaves me with 0.05714. Okay, so those are your molarities of your acid and your base. And these are important values because when you're going to calculate the pH, you need to know the acid and conjugate base concentrations. So I just kind of filled those in already. We'll ignore So this is the equilibrium calculation. We'll have to use the Ka value. We're going to ignore the water. We'll assume the hydronium is 0. So this is going to be minus x, and this will be plus x, and this will be plus x. So this will be 0.01428 minus x. This will be 0.05714 plus x and x. So I'm going to write Ka, which is this, right, is equal to the concentration of the products of the reactant. So I'm going to write 0.05714 plus x times x divided by 0.01428 minus x. And run it through a solver, and what you'll find is that x is 2.235 times 10 to the minus third, and so your pH will be negative log of that value is 2.65, like that. Okay. Again, it's very similar to the last chapter's problem, except for now we have a starting amount of the conjugate base. So kind of go back over what we did, and we'll look at some other examples as well, but look back what we did. We had the weak acid and the strong base, right? We calculated millimoles of each, calculated total volume. And then we did the limiting reactant. We found out there was a little acid left. So this is an important point to make. If you have acid remaining, you're going to be using this the acid ionization equation on the next page. And we had some conjugate base. Now, because we got to do an equilibrium calculation, and those are all done in molarities, we calculate molarities of the acid and the conjugate base. And we start a new ice table. And remember, this is the acid ionization reaction, not the titration reaction. So it is the Ka reaction. So it's the acid plus water. And then we set our quantities into the ice table to initially, and we just assume it's going to the right, minus x, plus x, plus x, and it gives me these values. I set it up into the equilibrium expression, setting it equal to the equilibrium constant, and then I solve for x, and then I convert that into pH. Okay, so what we're going to do is now move on in the titration to the next spot, right? So this is the point where we've added 12.5 mils of titrant. My total volume is the 12.5 plus 25, so 37.5 milliliters. And then I need to calculate the starting amounts of acid and base, right? So I have, I have 2.5 here, because again, it's just these two values multiplied together. I multiply these two values together, and this also comes out to 2.5. So now we know it's the situation where they're both going to run to 0, right? So it's minus 2.5, minus 2.5. So I have 0 and 0. This is an important thing to recognize, is that now all I have left is conjugate base. So this is plus 2.5. Started out as 0 before the titration started, and so I have 2.5 millimoles of conjugate base in the solution. Now, here's an important concept. When, right, the weak acid is gone. So when the weak acid is the limiting reactant. And again, how do you know that's the case? Well, the value goes to 0, right? The next page, we're going to do the Kb equation for the weak acid. So we're going to do Kb for A minus. Okay, so we'll get to that in a second. So, but the only thing to calculate the molarity of is this value here. So it's going to be 2.5. So this is the molarity of ClO minus or A minus, if you're ahead of me writing this down. Then it's going to be 2.5 millimoles, right, divided by 37.5 milliliters. And so that's going to come out to, and you can see they're on the slide already, 0.0667 molarity units of the conjugate base. Okay? And just a side note, in case it's confusing to you, this says NaClO, right? But this is the conjugate base that we're talking about. The molarity of this ion is the same as the molarity of this compound because of the one-to-one correspondence of moles of ClO minus to sodium chlorides. Okay. Yeah, so I filled that number in already on this ice table. But notice this is the Kb expression, and Kb is what you use anytime the weak acid runs out. So either they're both limiting or there's an excess of hydroxide. In both of those situations, this is the equation that you'll use to calculate your pH with. So, having said that, we ignore this column, right? This is minus x. This is plus x. This is plus x. And we're going to assume that there's no acid left because we just titrated it away, right? And there hasn't been any hydrolysis yet, so we have no OH minus or negligible OH minus. So this is going to be 0.0667 minus x. And this is going to be x and x. And again, this is going to set up like, oh, sorry. I want to write this out too because it haven't been a while probably since we've seen this. But HA, right, times OH minus divided by A minus. That's your Kb, right? And so that number is Kw over Ka. So you have to go back and plug in for this value 1.1 times 10 to the minus 2. That's from the previous slides right here. And then we're going to plug in our value. So I have Kb is equal to x times x, so x squared, right, because that's these values that are down here, divided by 0.0667 minus x. That's going to be equal to 9.09 times 10 to the minus 13, so it's pretty small. You can do the x is small approximation with this if you want, but you'll find that x is equal to 2.46 times 10 to the minus 7. And that's this value, right? So what you want to do then is you want to calculate the pOH. That's the easiest thing to do. And that'll be 6.61. And then the pH is 14 minus pOH. And so that'll be equal to 7.39, like that. Okay? So slightly higher than neutral. And this is generally the case when you're past the equivalence point or at the equivalence point of a weak acid titration. The pH will be greater than 7. All right. So the last point to check is what happens when you're well beyond the equivalence point. Okay, so for this problem, I want you to go ahead and fill in the ice table and get to the final concentrations of whatever's left in solution. Go ahead and pause, and then I'll talk you through it when we restart. All right, so here it is. Just worked it out. You got the total volume. This is kind of the normal, right? Total volume, 50 mils. Just add the two together. I have 2.5 mils, 25 times 0.1 of the weak acid. I have 5 millimoles of the strong base. So the weak acid is the limiting reactant, runs out, goes to 0. My change is minus 2.5, right, because that's how much I had. And then I subtract 50 minus 2.5, I get 2.5 again. And then the conjugate base, the chlorite ion, starts at 0. And then I add 2.5, so I end up with 2.5. So the molarity calculation is pretty straightforward then. It's the 2.5 millimoles of strong base that I have over here, divided by 50 milliliters, which is the volume that I have, my total volume. And that leaves me with 0.050 molarity units. And I didn't actually do the calculation for the A minus because I noticed that they were the same, so it's going to be the same. So those are my concentrations. And now I need to stick them into an ice table. And the thing you got to be aware of, again, and I'll just say this because this is a falling down point, right? That's telling me use KB reaction. All right, so we'll move on to the next one where some of the data has been filled in for you. So I did a KB, and I have a place to put my OH minus on the right side. I have a place to put my chloride ion on the left side. We'll assume the weak acid is 0 at the beginning, right? And go ahead and finish this out. The answer's on the slide, so you can take a peek at it if you get stuck. But I'll fill it out, and then when you go ahead and pause, and then I'll fill it out. And when you restart, we'll go through the answer. Okay, so I got to here, right? I just filled in. This is minus x and 0.05 minus x, and this is x and x and x and 0.05 plus x. Plug those into my KB expression, set those equal to 9.09 times 10 to the minus 13, and my x is 9.09 times 10 to the minus 13. And you're like, what? Isn't that just KB? And it is, in fact, just KB. The k is really small, right? So we can assume x is small. So this becomes x times 0.05 divided by 0.05, and so they cancel out because these x's are very small compared to 0.05. Now we need to calculate our POH, and that means it's the negative log of 0.050 plus something that's really tiny, right? 10 to the minus 13, so we're going to ignore it. Maybe 10 to the minus 12 if you're generous, but yeah. So you end up with a POH of 12.70 and a pH of 1.30. Now I wanted to make a point about this. You notice that we just calculated the pH essentially from the amount of hydroxide that was left after the titration was done. And this is generally true once you're about 1 milliliter past the equivalence point for most titrations. The pH of the solution is almost always determined by the excess hydroxide that's in the solution. Okay, so let me say that again. If you're past the equivalence point in a problem, like we are here, you have more sodium hydroxide than you do of the weak acid in the titration. The pH is almost always determined by the excess hydroxide. The hydrolysis caused by the weak acid adds so little hydroxide to this reaction that it's essentially negligible in almost all calculations. And like I said, really, by the time you're 1 mil past the equivalence point, that's almost always true. Okay? So we're going to summarize this and look at some of the data side by side and have a short discussion, really a monologue since this is recorded. Okay, so we normally leave all those calculations on the board in class, and we just sort of wrap around the room as much as we can and use little nooks and crannies. And then we write down all these values into a little table. So for the strong acid, strong base titration, we calculated 4 pH values, and those would have been 1.00, 1.85, and then 7.00, and 12.70. And then for the weak acid strong base, and we just did, we would have had 1.55, we would have had 2.65, and then 7.39, and 12.70. So let's take a look at this and see how these are different, right? So before the equivalence point, and even at the equivalence point, the pH of a weak acid will always be higher than the analogous point in a strong acid titration. And that really just makes sense, right? Because it's a stronger acid, and so its pH should be lower. But once you're past the equivalence point, the pH becomes the same because this pH, right, past the equivalence point, is all determined by excess base. This point, this is at the equivalence point. The strong acid, strong base is exactly neutral. It's pH 7. But at the equivalence point for a weak acid and a strong base, the pH will be higher. And this happens because of hydrolysis caused by, I should say caused by, not of, the A minus in solution, the conjugate base of the weak acid. Okay, so you produce this conjugate base in solution. At the equivalence point, technically you've reacted all of it, but some of it back reacts. It reacts with the water that's surrounding it, and it causes a little bit of hydrolysis. That means you're going to have excess hydroxide in the solution, and your pH will always be higher at the equivalence point for a weak base, okay, or weak acid. Now, during the titration, right? And this is kind of an interesting way to think about it. If you know, like, the equivalence point is going to be 7 here, right? Then you know for the weak base, you can predict it'll be a little bit higher. Now, how much higher it actually is, you can kind of guess, and I'll show you that later by doing a calculation based on midpoint pH. And what the pH is at the end of the titration. But it turns out this number is usually about halfway between the midpoint pH and the equivalent and the endpoint. The final pH of the solution. So, you can only practice so many problems, and so what I did was generated a graph like this. I actually stole this from an old textbook, and it gives you the pH at a bunch of different points. It's for 25 milliliters of 0.1 molar sodium hydroxide. I don't think that's on there anywhere. And 0.1 molar hydrochloric acid. So if you really want to practice, see, like, if you could calculate it at 20 mils or 35 mils or 10, this data should allow you to do that. Okay, so it's just there for an example. And it gives you the pHs at different points so you can really practice the calculations.